So I wasn't sure.
Yeah, so we'll, this is a problem 5.4.13, okay? And so this, it says we have a sample size of 50, okay? Size equals 50, so I'm just jotting these as comments to myself. And so one of them is, so we want to know 80% or more, okay? So I mean, sorry, and the probability that a mussel will be infected with a parasite is 0.8, okay? And so here it says, take a random sample of size 50, find the probability that fewer than 35 of the sampled mussels will be infected, okay? So in this case is probability that that fewer than 35 are infected. So the answer to this is going to be P by gnome. Okay, this is going to be the true answer. It's P by gnome because that's going to be the sum from 0 up to whatever number I specify. So what number am I going to specify here? 34. Okay, I'm going to specify 34 because that's going to give me the sum from 0 to 34. And size is 50 and probability is 0.8. So the answer that fewer than 35 being infected is going to be 0.0308. Okay. I don't know. Does that look familiar?
Yeah.
Does that look right? Okay. So that's going to be the answer. Now, if you want to do it manually, it would be very painful because you'd have to do the binomial probability for 0, binomial probability for 2, all the way up to the binomial probability for 34. Now, at a certain point, I guess you could start at 34 and work backwards. At a certain point, they kind of just all run to 0 anyway. We could also approximate this using the normal distribution. Okay. Sorry.
Settle down.
Okay. And so our normal distribution will have mean what? Equal to n times p, which is 50 times 0.8. So that basically, let me just write m is going to be equal to 50. Here, I'm just going to say n is equal to 50, p is equal to 0.8. The mean is going to equal n times p. And so that tells me my mean is 40. And then the standard deviation is going to be equal to the square root of n times p times 1 minus p. Okay? And s is that. Okay? So all of these, I mean, I could punch these out into a calculator myself and get these numbers, but because R, you can just use variables and just plug them all in here, you can get all of these things. Okay. So we have that. And then so if I wanted to do a normal approximation, so part A says normal approximation without continuity correction. Okay. This is actually a little bit ambiguous, right? Because if I'm doing it without the continuity correction, should I start at go from 0 to 34, or should I go from 0 to 35? Okay, and that's the question because we're doing it without a continuity correction. So I don't know if I need to. Sorry to the people watching the video only. I'm drawing a thing over here. Okay. So according to the normal, our mean is centered at 40. Okay, and we have. We basically have bars centered at 40, okay? And over here, I've got 34 and I have 35 somewhere, okay? And just imagine having a bar centered at 34 and a bar centered at 35. And so if I want all the bars that go this way, I would shade in the entire 34. And we can see that I would draw a cutoff at 34 and a half. But without the continuity correction, I could choose either 34 or 35, and they would be equally valid. So I could do P norm 34, and my mean is n, and my standard deviation is s. Okay, so I could put in actual numbers, but because I also told R that n is equal to this value and s is equal to this value, I can just plug things in there. P norm 35 will give me this, and the true answer, so this is with the continuity correction. Use 34.5. This is my answer. Okay, and what was P binom? Okay, so this, so the answer is it's a little bit off. Okay, it's not quite, it's not completely the same, but you know, and this is mostly because we're towards the end. If it was closer to the middle, like closer to the mean, the approximation would be better. Okay. But I don't know. Do these numbers kind of look familiar to what you guys saw in your lab? I hope. All right. Okay. Are there questions from the lab, or why we, or just even from this part, why we chose certain numbers and things like that? Okay. Sometimes they wipe all of the information off these computers and reinstall everything, but then they forget to register products. Alright, so today we're going to dig into chapter 5 and chapter 6. Okay, and chapter 5 is on sampling distributions. So last week we learned about the normal distribution. And the normal distribution was, you know, we said people's heights followed the normal distribution. And we can, if I pick a random person, and if I knew the mean and standard deviation, we could figure out what percentile this person was in, right? Or if I said, give me the height of someone in the 30th percentile, you could also figure that out using the normal distribution. But now we are not dealing with individuals. So last week when we had the normal distribution, I would say here's an individual. This person's IQ score was this. What is their percentile? Or here's another individual. This person's height was this. What what percentage of people are taller, or what percentage of people are shorter, or what percentage of whatever you're measuring. If it's normally distributed, okay, we could ask you things like what percentage of people are within a certain range, and you could use your normal table and figure that out. Okay, so the normal distribution allowed you to figure out basically these percentages for individuals. What percentage of individuals fell within a certain range or something to that degree. This week, it's different in that we're looking at sampling distributions, and we're trying to not understand the distribution of an individual's measurement or score, but we're trying to understand the distribution of a sample's score. Okay, so let me just write that up. Okay, so last week, the normal distribution individual's height or score measurement. So last week we would say something like IQ follows the normal distribution with mean 100 and standard deviation 16. What percentage of people have IQs over 110? Okay, we can do that. This week, for sampling distributions, tell us how measurements from a sample are distributed. Okay, so let's just put on do kind of a thought experiment, okay? And this is a thought experiment because this would never be done. Well, not never, but generally this is not done in real life. Okay? Alright, so here's the population. This is everybody. Okay? And so let's say we're looking at IQ scores. Okay, so in the population, the IQ scores follow a normal distribution with mean 100 and standard deviation 16. So this is everybody in the population. Somehow we know this. But now I'm not going to draw out one person at a time. Let's say I draw out 10 people. Okay, I take a sample of 10 people. Okay, so n is equal to 10. These are 10 people taken from the population. And we figure out everyone's IQ. And from this, I just say that the mean of this sample, I get an x bar or a y bar. Let's move this y bar. Okay, so this is the mean of a sample. Okay, what value might y bar be? It could be anything, right? Huh?
Something near 100?
Yeah, something close to 100, right? So it's the average. So we took 10 random people, and we measured their IQs, and we took their average. So we're expecting something close to 100. Maybe it's 101, maybe it's 100, maybe it's 99, 98. Okay, it's some value, all right? So let's say it's 98. I'm just making up a number here. Or 98.4. All right. Let's take another sample. Okay, so we throw these people back. It doesn't really matter. Okay, this population is really big. And I take another sample of n equals 10 people. Okay, so this is another sample. And from the sample, I also calculate another y bar. Okay. What could we get this time? Maybe the average is 2.5. Who knows? Alright, and then we do this again. I take another sample of n equals 10, and from the sample, I calculate a y bar. Do it again. And I get a y bar. And let's say I do this many, many, many times, okay? Many samples, many y bars. Alright. So, say I've got tons of resources and I can do this all day or many times. And let's say I created a histogram of all of those y bars. Okay, so let's make a histogram of the y bars observed. Okay, so let's say I do this. We do this maybe 100,000 times. We generate. Maybe that's not even necessary. Okay, let's say 30,000 samples of n equals 10. Okay. So how many y bars would I have? I would have 30,000. And let's say I make a histogram of all of these y bars. What is this histogram going to look like? Any ideas?
Bell curve?
Okay, so we think, we suspect it would look normal, okay? So probably normal. Okay, well let's try this out. Okay, so I'm going to do this in R here, okay? And so what I'm going to do is I'm going to create a population. I'm going to call it a population. And in the population I'm going to have, I'm going to just generate let's just make 50,000 people. this is the histogram of everybody. Okay, this is 50,000 people. We can see that the mean is 100, standard deviation 16, and we can see, yeah, most people are between IQs of 80 and 120. Okay, but we have some people who have lower IQs and some people who have higher IQs and things like that. All right. So what are we going to do now? So let's keep this in mind somewhere. Let's see if I can export this. Okay. So what I'm going to do is I'm going to generate a sample. Okay. And so from sample, if we look at what population is just a list of 50,000 different values here. Okay. And so I can just say population. Alright, so here's 50 people from actually these are the first 50 people that exist in population, and these are all their different IQ values. Okay, and it's continuous, so we have decimal IQs. Alright, so anyway, let's say I can take a sample from population. I forgot how to use sample. Okay, yeah. And what sample population does, okay, sample says take a sample from whatever you put here, okay? And so here, population is a list of 50,000 different IQ values, okay? So population is just this giant list of 50,000 IQ values, and sample says go into that giant list and take out this many. So I'm just saying take out 10 people. Okay. And what that does is here are 10 random people. Okay. So I mean, so just so you know, sample. It's like I could. There's something called letters. This is just the letters of the alphabet, and I could just say give me 5 letters from the alphabet, and it will pick 5 random letters from the alphabet. And every time I do this, it's going to give you 5 different letters from the alphabet. Okay. And so when I do population sample population 10, it's just going to give me 10 different people from that list of 50,000. Okay, is that okay? How sample is working? Yes.
Different meaning it won't ever repeat one of the.
Yeah. So whenever I give the computer this request sample, I say just take a sample. It understands. Okay, generate. Basically, in the background, it's generating there's some random method that it's using to pick out individuals here. Okay. Yes, Bill.
So when you put sample population 10,
Yeah.
is it actually generating 10 new random numbers, or is it actually pulling from a pool of 50,000?
Yeah. So I created this pool called called population. So my population has 50,000 individuals in it, and it's pulling 10 people from this pool of 50,000. Okay, it's not trying to generate 10 new ones. Okay, the generation of 10 of the people happened at this very early command called rnorm. Okay, and this says generate random numbers that follow a normal distribution with mean 100, standard deviation 16, but how many? 50,000. So the generation of the random numbers came here, okay, and this is to simulate that there's 50,000 people that follow a normal distribution.
So there's actually 50,000 numbers cached on the computer.
There's 50,000 numbers cached here.
Okay.
And inside this variable called population. Okay, so the computer has stored in its memory 50,000 people. All right. Now it sounds like a lot, but for computers, it's not a lot of work at all. Okay. Yes.
Does it set a high and low limit?
No. So technically, it is possible that we have people with negative IQ values. Okay. And technically, that's not possible in real life, but because the normal distribution does go from negative infinity to positive infinity, it is possible that someone has a negative IQ. But that means they would have to be at least 6 standard deviations away from the mean, which generally happens only about 4 in a million, so, so it's possible, we might have gotten that.
So it could spit out a value of like 600 and just
It
kinda
could,
have to
it
deal with
could,
it.
yes, when you do this, yeah.
So if you take a sample, you don't have to specify for it to be random in general, it does
Yeah,
that.
sample is always going to be random. So the command sample, built into it is take a random sample. So command sample means random sample. If you wanted to select members individually, you'd have to specify which ones you want to select. And there's selection commands here, but when you use the command sample, it tells the computer select randomly. Okay? Okay, and you don't have to understand all of these things, but I'm just trying to show you what I'm doing here. So when I show the results of doing this thing, it's not like, well, here's a picture and here's another picture, and ta-da, you know? Okay, so what I'm going to do is I'm going to write just a short little script, okay? And basically it's going to say, I want you to do the same process many times, okay? And the process is take a sample, and whatever sample this is, calculate the mean of the sample, and record the mean of that sample into another, into somewhere on the computer so we can keep track of it, okay? And I'm gonna tell the computer, do this 1,000 times, or do this 10,000 times, it doesn't really matter, okay? So again, the command I'm gonna write is, take a sample, just like this, where it's just drawing 10 people from this cache of 50,000. Calculate the mean of that, and store the mean somewhere. So, I'm going to create basically a vector called, or a variable called, what is it called? I'm going to call this means. Okay, and just by putting in 0, it's created it. Okay, so right now means has the value 0, but I can start sticking things into it, and I'm going to create a loop. So I'm going to just say for I in 1 to 10,000. Okay, and it says. So I don't know if you guys are familiar with loops or at all, but don't worry. I'm going to just say. Take a sample. Of size 10, and I'm just throwing it into a temporary thing called D. And then what I'm saying is, take the mean of D, of that sample of 10, and store the result in means. It's going to complain that it doesn't have. Maybe it won't. Okay, and that's it. It's done. It did it 10,000 times. It took a sample of size 10. Each time, it stored it into a temporary thing called D. Then it calculated the mean of D, and it put the mean of D into this variable called means. And basically, by having the I in here, the first time it did it, it put it in the first position, and then the second time it did it, it put it in the second position, and so on and so forth. Okay, so then when I look at up here, this is all of the basically things that it's stored in its workspace. We can see means is a numeric vector, and there's 10,000 values in it. So now I can look at the histogram of means. Is this comfortable, or if anything sounds weird or whatever, just please raise your hand and I'll try to explain as best as I can. Yes, sir.
No, I'm just following it, sorry.
Okay. All right. So let's take a look at this. Okay. So let's take a look at histogram of means. No. Okay. So it looks like a normal distribution, just like we had before. Okay. But what do we notice kind of about the range here?
Pretty small.
Huh?
Much smaller.
It's much smaller. It's much smaller. So before, let's do this for the top here. Okay. So this was the first one that we saw, okay? And we could see that this is the when we looked at individuals, it seemed to go maybe not to 0 or negative numbers, but maybe 30, okay, up to maybe 170-ish, okay, somewhere around there. So when we looked at just individuals, we didn't have very many, but there were a few individuals with IQs of about 50 or 60, and there were a few individuals with IQs of about 140, 150, okay? But when we look at this, where did it go? Okay. These are the IQs of samples of size 10. Okay, and so when we took samples of size 10, we don't see any samples where the IQ is 150 or the average IQ is 40. Okay, we see some samples where the IQ is maybe 112, 115. This might even be like 118, but these were extremely rare. Okay, in the 10,000 times we did it, this probably happened once or twice. Okay, so to get a sample of 10 people picked at random where the average IQ is 120 seems to be a very rare occurrence. Okay, and if we think about that intuitively, that also kind of makes sense, right? If you were to just pick 10 random people somewhere, it's unlikely that the average of all 10 people is going to be like 120, like significantly above the average, okay? Anytime you take a group of people and you look at the average of that, we're expecting is going to be close to 100, and that's exactly what we see. Okay. What would happen if, rather than taking samples of size 10, I took samples of size 100?
Would narrow the range even more.
Yeah, the range would get even more narrow. Okay, so and we can we could calculate some statistics here. Okay, so means is just a vector of 10,000 values, and I could say, what is the mean of all of these means? Okay, so this is the mean of all 10,000 sample means that I've observed. Okay, so this is the mean of the 10,000 sample means. Okay, and that was 99.95, so very close to 100. Okay, we actually didn't calculate the mean of the population because it might not necessarily. It's not going to be exactly 100 anyway. So the population was 50,000 people. If I asked what's the mean of the population was 100.0085. So just a tiny bit more than 100. Okay. And I can ask, what was the standard deviation of the population? Should be something close to 16. Indeed, it is. Okay. But let's ask, what's the standard deviation of all the means? And we see that number is a lot smaller, about 5. So if I did this whole process again, but rather than taking a sample of size 10, I took a sample of size 100, what do you think will happen? Our standard deviation will get smaller, the range will get smaller, and indeed we will see that. I'm just going to put in 100 here. I'm going to run it. And then, so let's take a look at the histogram of means. Okay. And indeed, we can see it's even, the range is even smaller, going from 94 to 106. Okay, we rarely saw the average being 106. Okay, most of the time it was like 99 or 101. We can ask for the mean of the means. Still very close to our population mean, and we can ask for what's the standard deviation of the means. And indeed, we see this is even smaller at 1.6. Okay. Yeah, we have a question.
Why in this case, for the histogram, are the bars not centered over the numbers?
So regarding the histogram, the rules of creating a histogram are different, okay? You don't have to have them centered over the numbers, okay? I say that to kind of explain how the binomial distribution works, okay? And in actuality, the binomial doesn't even have bars, they're lines. But I think it's easier to visualize a bar here, okay? So regarding a histogram, you could have your bin start at any number you want. If you wanted to start it at half numbers or 100.2 or 100.6, you can. And there's no rule against it. It's just, you just have to count how many fit in a certain bin. So the computer kind of defaults to doing it this way. But there's, when I say bar centered at a number, that's more so just something I'm saying to help you understand the binomial there. Okay. All right. Okay. So this. So that's that. Okay. Is that all right? Okay. What would happen? So if we think back to what our population looked like. So let's make a histogram of our population then. Our population itself was normally distributed. Okay. So it kind of made sense that when we took out samples from this normally distributed population, and we looked at all of the means from here, that our thing would end up looking normal. Okay? What if our population was not normal? What if we had a uniform population? Okay? So uniform means all of the numbers are equally likely to show up. So let's say I said we went out and we asked 50,000 people, what is the last digit of your cell phone number? Okay. And some people are going to say 0, and some people are going to say 8, and some people are going to say 3. And we would expect that approximately the same number of people who say 0 will say 8 and will also say 3. Okay, about the same. So, because as far as I know, when it comes to the last 4 digits of your phone number, they just kind of take whatever's available out there and give it to you. Okay. All right, so I can generate this, and population is now going to be something. Sorry, I just want to make sure I'm doing this correct. Alright. For some reason I'm having trouble getting, maybe I have to do, Alright, so I was trying to generate a whole bunch of numbers, but I think, you know what, for whatever reason, I think this is just a graphic artifact. I think all of the numbers do show up equally, but for whatever reason, it's putting the breaks in the wrong order. So this bar should be pushed down, and that would shift everything over and push this bar up, so it's equal. And for whatever reason, I'm just having trouble with the histogram. And but I can so if I look at population, okay, I can ask how many in the population are equal to 0 and how many are equal to 1. Yeah, you know what? That is different. Okay. Let me just try to generate my population again, and I'm sorry about this. Oh, I see. It's not round, but I want it on floor. Okay, that works, that works. Sorry. So here, I've just, if you want to know the technicals, okay. Basically, by using round, everything that was like, if the, so our uniform generates numbers between 0 and 1, okay, all equally likely, and I multiply that by 10 and I had it rounded. So when a number was generated and it came out to be like 0.6, it would round that up to 1, okay, and so things got messed up, and so now, but by doing floor, it should even out, and so if I do histogram of population, there we go. That's what I wanted. Let's say breaks equals. And this for sure is just an artifact of what's happening. Okay. Well, anyway, here the bars are all about the equal heights, and it's just there's a weird spacing thing going on here. Okay. But, so anyway, the numbers are all here. I've got about the same number of zeros as I do have 2s, as I do have 4s, and 9s, and things like that, okay? So what if I do the same type of thing here, and I'm drawing a random sample from here, and we look at the average of the sample, and we do this over and over again. So I do the same type of thing. I take a sample of 10. I ask 10 random people, what's the last digit of your phone number? But then I average those numbers, and I record it. I ask another 10 random people, what's the last digit of your phone number? And I average it, I record it, and I do this, let's say 10,000 times. What's the distribution going to look like that? Yeah.
Should look the same square-wise, but with a smaller standard deviation again?
So you think it'll also be uniform?
Yeah.
With a smaller standard deviation. So what would my range be on that though?
Shorter.
Shorter. So is it possible for me to select 10 people and get an average of 0?
Likely, but yeah.
It is possible. It's not. Or 0.1 or something. Okay, not likely, but it's possible. Is it possible for me to pick 10 people and get an average of 5? Is that going to be more likely?
Mm-hmm.
Okay, what about 10 people and getting an average of 9 or something close to that? Okay. Alright, so when we think about this, we have a suspicion that 5 is going to be a little bit more likely than 0 or 9. Okay. So let's see what happens. Let's see what happens. Okay, so we're going to just do the same thing. Samples of size 10. Let's run this. Okay, now let's look at the histogram of the mean. Okay, what does this look like? It looks pretty normal. It looks like we got a normal curve going on. let's try this again. What if I take only samples of size 2 though? What's this gonna look like?
Get more realistic. Might get more realistic.
More realistic? What does that mean?
Less normal.
Less normal.
Less centered around the center value.
Okay. With samples of size 2. Okay. So another way to think of samples of size 2, when we have so the histogram of our population. Histogram of our population shows that each number is about equally likely to show up, right? So just think you've got a 10-sided die here that have the numbers 0 through 9. Okay. But now you're playing some weird game of Monopoly where you take 2 and you're rolling them. Okay. Okay. Or if they introduce this game at Las Vegas, which is the number that everybody's going to be betting on? Well, not the sum, but.
10.
Okay. Well, let's just see. Let's just see what happens. Okay. So we run this. Let's make a histogram of all of our means. Any question? Any idea? Who thinks what this is going to look like? It's a pyramid. We get a pyramid here. So what's going on here? Okay, so we got the digits 0 through 9. Okay. And the most likely thing is getting an average of basically 4.5. 4.5. Okay. And that is because that can happen 10 different ways. You can get one person with a 0, one person with a 9, one person with a 1, one person with an 8.
Oh, because you're summing the two dice,
Yeah,
right?
you're summing the two. Yeah,
Okay,
you're
okay,
summing
I
the.
was
Yeah,
thinking
because we're taking the
total
average here,
randomness,
right?
Okay.
We're taking the average here. We're adding the two dice and dividing by 2. Okay. So this can happen 10 different ways. Okay. How many ways can you get an average of 4? Well, you have to get 0 and 8, 1 and 7, 2 and 6. Sorry, and so on. Okay. And there's only 9 ways for that to happen. How many ways to get an average of 5? Okay. Well, there's only 8 ways for that to happen. Okay. And so as you go out, the only way to get an average of 9 is if you pick someone with a 9 and someone else with a 9. And whatever. This is a result of randomness. So here's an artifact. If I did this all over again, the shape would be very similar, but not exactly the same. Okay. Well, we're still getting this weird thing where 0 is a little bit high. Yeah.
Yeah, I was just about to say, is there a reason why it's like artificially distributed around 0 higher?
I don't know. I don't know what's going on there. Okay. It shouldn't be.
Is it including the negative numbers? Is this
I don't think so. I think let's look at our population, and if I just ask how many in our population is equal to 0 versus 9 versus 1. Now they look all about the same number in each of these. So I don't know what's going on there. Okay, but whatever. So that's when we did populations of size 2, and we can see here's what happens when we do populations of size 3. Okay, so slightly odd. Again, that's an artifact of the thing here, but. And then we can see at 4 it starts getting kind of curvier, and let's just see what happens when so I'm going to bump it up to 10. And at a certain point, and pay attention also to the range on the bottom there. Okay. We're still keeping things that are, the shape is normal. The shape is normal, but then the range gets kind of smaller and smaller. Okay, and I'm sorry that the bars keep changing thickness here. So we see kind of this interesting thing where at a certain point the end result ends up looking normally distributed, but then and the range keeps getting smaller and smaller. But when we had only samples of size 2, it was clearly not normal. It was very much a triangle, okay, or a pyramid. Okay, so let's discuss. Okay, and all right. So, well, were there any questions from the computer or the simulation, or what? I'm hoping that illustrated this concept up here of the sampling distribution. At least where it's coming from. So let's talk about the sampling distribution. Okay, so the sampling distribution. The sampling distribution of y bar is it's technically the theoretic distribution, okay? That is the and then a note is just assume when we're talking about a sample distribution, we have to assume a constant sample size. So when I took samples of size 10, that creates one sampling distribution. When I took samples of size 2, that created an entirely different sampling distribution. So the samples of size 2 generated the sampling distribution that looked kind of like a triangle or a pyramid, whereas the samples of size 10 created one that was looking like the normal distribution. Okay, so you can't mix sample sizes and talk about the same sampling distribution. If you change the sample size, you got a totally different sampling distribution. Okay. All right. What we saw was that at a certain point, the sampling distributions looked like a normal distribution, and that's the case. Okay. That's known as the central limit theorem. Okay. Basically, this says the sampling distribution of y bar, or the sample mean, will the normal distribution is defined by, every normal distribution has two parameters that define it. And what are they? Well, when you had the mean and the standard deviation, okay? So the mean, okay, so this normal distribution for the central limit theorem, the mean will be, what will the mean be? The mean will be the same mean as the population, okay? The mean will be the same mean as the population. And the standard deviation of this normal distribution will be the population standard deviation divided by the square root of n. And we kind of had some kind of sense that something like this was going on, where we saw that when we increased the size of the sample, made n larger, the standard deviation, or basically the spread, was getting smaller, okay? And so, and that's reflected in here. The standard deviation is the population standard deviation divided by the square root of n. So when we took larger samples, this square root of n number got larger, and this is on the denominator, so the standard deviation would shrink. There's a squeal, right? Yeah. Nice. So this says y bar follows. So I'm just summing this up with symbolically. Y bar will follow the normal distribution with mean mu being the population standard deviation. I'm sorry, population mean. Sigma is population standard deviation. So y bar follows the normal distribution, mean mu, and sigma over the square root of n. Okay. But we have conditions that need to be met. Okay. So the conditions for this to be true. So one is that our samples, when we select the samples to generate this, they have to be random samples. So they have to be randomly selected, and the selection of each person must be independent of the selection of other people. Okay, randomly selected, and selection process. Selection is independent of other selections. So if somebody is selected, they can't change whether the probability of that person's brother is selected. Okay, so the probability of selection must remain constant throughout, and they must all be randomly selected. And here is that the sample can't be too big, but the sample can't be too small. Okay. this is rarely a problem for your sample size to be too big. Okay. And for too big, the general rule is don't select more than 10% of your population. Okay. Because once you select more than 10% of the population starts to look different, right? So if we talked about, I've got a deck of 52 cards, what's the probability that I select a red card? You would say 1/2, okay? But after I've selected one red card, and ask you what's the probability that I select another red card, it's no longer 1/2, it's 25 out of 51, okay? And for our sake, that's close enough to be 1/2, where we can kind of ignore it. But once you select more than 10%, so once you start selecting like more than 5 cards out of a deck, the proportions and the things of what's left in the deck changing enough where we can't ignore that effect anymore. Okay, so that's why we say the sample must not be too big. But here we're talking about, like, usually you're taking samples from the entire country, where you're not going to be worrying about taking a sample of more than 30 million people or something like that, right? So this is rarely a problem. Sometimes it is. Okay. The other one that we face is that the sample must not be too small. Okay. Not be too small. Okay, or the sample has to be big enough. All right. So here we break this down into 2 parts. Okay. If the population is normal, okay, so this was like the IQs. If the population is normal, any sample size is fine. Okay. There's no sample size that is too small for a population that's normal. Okay, because at the heart of it, if you select an individual from a population that's normal, then you'll just have basically the distribution of the population, and that's normal. So we don't have to worry about that. Okay? But if the population is not normal, your sample has to be bigger. Must be larger. Okay. And we kind of saw this with the uniform population. So when we were looking at the population of cell phone last digits in a cell phone, okay, we saw that when we selected a sample size of 2, that was too small because we ended up with basically a pyramid or a triangle, which is clearly not the normal distribution. But around selecting a sample size of 4, it started to look kind of normal, and there's kind of a judgment call: is this normal enough or not? Okay, and I think in your homework they talked about normal probability plots, where that can be used as a tool to assess normality. Okay, and basically you just give computer data and you say, give me a normal probability plot, and you look at it and you say, it looks normal. Okay, some of these things are subjective.
Is that what it really comes down to? Is it just kind of a subjective evaluation of whether you feel like, oh, it's kind of normal or not?
Yes and no. Okay, there are concrete tests that will give you some kind of number, and we've drawn arbitrary lines that say at this number we're going to say it's normal, and at some number we're going to say it's not normal. But I mean, everything is kind of a judgment call, right? Like, so we say at age 18 you are an adult, okay? But some people will say, and some individuals, they might be mature enough to fully understand adult consequences and decisions at age 17, and other people, they're like 23 and they still haven't fully understood, you know, consequences and things like that. So, you know, everything's a little bit subjective, and that's true for all of life. So, but yes, so statistics especially so. But yeah, I know that's kind of a little unsatisfying, but that's how it goes. All right, so if the population is not normal, the sample size must be larger, and basically, so we only looked at two distributions. One was the normal one, and then one was the uniform. Okay, but there's all sorts of other distributions. Okay, you have bimodal distributions, and you have skewed distributions, and you have all sorts of crazy distributions. Okay, and basically, the more not normal, or actually, the more skewed it is, or the larger the sample needs to be. Okay, most of the time, a sample size of 30 is big enough. Okay, but sometimes a sample size of 30 is still not big enough. Okay, so this is just a rule of thumb. So not always. N equals 30 is large enough for most cases. Okay. But basically, here, let me also write. If the population is very skewed, the sample must be even greater. And if it's really skewed, you might consider a transformation, like a log transformation or something. Okay, but so really skewed distributions need much larger samples. Things that are kind of symmetric-ish, 30 is going to be big enough for most situations that you deal with in life. Okay, but maybe like income distribution is really skewed. Sample size of 30 is not going to be big enough. Okay, you need like a sample size of 1,000 or something. Just because like income is one of those things that's so extreme. Putting people who make millions of dollars on the same scale as someone who makes, 10,000 is going to be very extreme. Okay, so that's okay. So that's sampling distributions. So let's just say let's try something out. Okay. So let's say IQ follows normal, mean 100, and size 16. I'm going to say I take a random sample. Say 25 people. What is the probability that the average IQ of these 25 people is over 104? Go ahead and try to solve this. You'll probably need your normal too. So, You guys have an answer? Let's see, actually I haven't done it myself, so. Okay, so IQ itself follows a normal distribution with mean 100 and standard deviation 16, okay? But here we're not looking at the distribution of individuals' IQ scores, okay? What are we looking at? We're looking at the distribution. We want to know what's the probability that the average IQ of these 25 people, okay? So this is a Y bar. So we want to know what is the distribution of Y bar, okay? Well, Y bar from the central limit theorem and what we understand about sampling distributions will follow what? The normal distribution. What's the mean of this normal distribution?
Same.
The same. So that's going to be 100. And what's the